Good evening, ladies and gentlemen. All right, so I have been challenged to a duel by the one Ranty Flat Earth. He has asked me to look at his observation from Nicky Nook across to the Isle of Man and scale each mountain against each other and try to work out the hidden amount. So I gladly accept your challenge. Thank you, Ranty. All right, so he sent me the composite image, which is looked to be stitched together nicely. I've identified the peaks. This one is Greba at 473 meters tall, all the way up to the tallest mountain, Snaefell, 620 meters and 119 k's away. Then I have zoomed in and as best as I could count the number of pixels between the horizon and the top of the peak. So Greba is the smallest in the image at 74 pixels, all the way up to Snaefell, which is roughly twice as big, at 149 pixels. Alright, so let's move over to Excel, and I will try my best to explain this spreadsheet. So the first three columns are really just the data that we got from Google Earth. So all the mountains, their elevation above sea level, and their distance from his observation point. And then my best measurement as to how tall they appear in the image. Currently we're looking at a flat Earth model, so there is no hidden amount, and that would mean that all of the mountain is visible. So plugging those numbers in, so 473 meters tall at a distance of 124 kilometers gives a visible angular size of 0.2188 degrees. And I've done that for each peak. Now what I want you to realize, which should be fairly obvious, that if you have a rectilinear lens without any distortion, that this ratio between pixels and the visible angular size should be a constant. Okay, so over here I have expressed that as a ratio of pixels per degree, which is just the number of pixels divided by the number of degrees that are visible. And our goal is to find the set of figures here that display the least amount of variance, and that will be the best description of the image, I guess is the way to say it. So currently at the moment we have all these ratios of pixels per degree, and the average of those is 420, but the standard deviation is 63. So that's quite a spread. The standard deviation has, I've expressed that in terms of percentage of the average as well, at 15%. So again, our goal is to have these as correlated and as equal as possible. So on a flat Earth, our single answer is that it is about 15%, and we're trying to minimize this number. All right, so let's flick over to our globe model. And currently we've got a radius set of 6,000 kilometers. So let's look back at our spreadsheet. So Greba Mountain, 473 meters, 124 k's. Excuse me, that has a hidden amount of 445 meters with this radius, which leaves only 28 meters, visible in the image. And 28 meters at a distance of 124 kilometers has this angular size. So this is a visible angular size. So the amount of the mountain that should be seen above the horizon. All right, so again, we express this as a ratio of pixels per degree. And as you can see, we have a huge amount of variance between 1,300 and 5,724 pixels per degree. So that is a terrible radius. All right, and that's expressed in this percentage of the average. So the standard deviation, huge relative to the average. So let's play around with our radius and see if we can set a radius such that these numbers are fairly consistent. All right, so we're at 58%, which is crap. It's far worse than the flat Earth calculation. So let's go up to 6,100 kilometers. And that's dropped down to 44%. Let's tick it up a few more, and we'll get to roughly the accepted value for the radius itself at 25%. So that's still far worse than the flat Earth. Let's see how we can go. Oh, so at 6,700 kilometers radius, we are roughly the same, roughly as accurate as the flat Earth calculation. Let's tick up a little bit more. Oh, it's dropping. So as this percentage drops, you'll see that these numbers are getting closer to each other. All right, so the standard deviation is only 84 against an average of 1,000. So let's tick up a little bit more. 7%, 6%, 5%, 4%, 3.5%, 3%, 2.6, oh, 2.5. All right, so now we've started ticking back up again. So let's tick back down. There we go. This seems to be our most highly correlated set of ratios here. And that happens when the radius is approximately 7,900. So you can either accept that the Earth radius is 7,900, or you can accept that the Earth radius is 6,371, but has a K factor, or an effective Earth radius of 1.24 times. But in any case, this result here of 2.5% is far better than the flat Earth result of 15%. So yeah, cop that, Ranty.